This is about using, this example is about using the constant heat flux condition. Let's say this question, we have water here. It's flowing at 0.1 meter per kilogram per second. And we have energy generation on the wall. And it's generating at 10 to the 6 watt per meter cube. And it's insulated at the very top. Okay? So the surface temperature, so we have inlet temperature 20 degrees Celsius, outlet temperature is 60 degrees Celsius, and the surface outlet temperature is 70 degrees Celsius. So the question is, what is the length in here? Okay. So what is the length that is going to satisfy this these requirements in here? Okay, so our goal is find L to heat fluid from 20 degrees Celsius to 60 degrees Celsius. And we know the mass flow rate is 0.1. So let's start with our assumptions. We'll assume this is a steady flow, and uniform heat flux. And an incompressible fluid. And the properties are constant properties. So T mean average is, we have 20 degrees Celsius inlet, 60 degrees Celsius outlet. So the mean temperature is 40 Celsius, which is 313 Kelvin. So at that temperature, water has a Cp of 4179 joule kilogram per Kelvin. So now we are going to use energy balance. So total energy generated within the system is energy generation rate multiplied by the volume where we have the energy generation. That is the peach color here. That is the area volume of the energy generation. And if you multiply that by Q dot, we get the total energy generation. So volume multiplied by Q dot will give us the total. This is the volume. So since this is a pipe, right? This is a cylindrical pipe. So we have inner diameter, outer diameter. I can calculate the volume simply by pi over 4, the outer square minus the inner square multiplied by L multiplied by Q dot. So this is going to give me the energy generation. And this is constant. So Q dot pi over 4 d square I square L is equal to m Cp Tm out minus Tm in. So that means L, the length required to achieve this, is mCp Tm out minus Tm in divided by Q dot pi over 4 the outer square minus the inner square. And here I do know everything. So I know the mass flow rate. This is 0.1 kilogram per second. Cp is given 4179 joule kilogram per Kelvin. Inlet and outlet temperatures are given 60, 20. Q dot is 10 to the 6. The outer is 0.04 square. The inner is 0.02 square. So we will get 17.7 meters. Okay? So this is the length required to achieve this. And if you want to calculate the heat transfer rate, if you want to calculate, for instance, convective heat transfer rate, so we have Q0. H0 is defined as heat flux divided by delta T. That is the definition. This is the definition. We learned this in chapter 6. So that means Qs divided by TSO minus TMO. If you want to calculate H at outlet, this is at outlet. So that means Qs, the heat flux, is energy generation per unit volume divided by pi DIL. So this is, so we have energy generated here. It's insulated from outside. So that means the surface area, inner surface area. If we divide this generation by inner surface area, we get the flux. And this is equal to Q over 4 d0 square di, the out square, the inner square over the I. So that means we have Q surface is equal to 1.5 times 10 to the 4 watt per meter square. So our goal is to find H naught at the outlet, 1.5 10 to the 4, this is the heat flux, divided by the temperature difference, 70 minus 60, we have 1500 watt meter square per Kelvin. Okay, so we just calculated the H0 at the outlet in the last part of the problem. In the first part we calculated the length, but we also wanted to calculate what is the H naught at the outlet. And this is basically, we use the definition of convective transfer coefficient. So heat transfer rate divided by delta T, and then we calculate heat transfer rate, and we have H naught.